Welcome students. We are going to have another interesting session on basic econometric model. Today we are going to see some of the symbols that are quite often used in econometric models and the types of such regression models. Now let us take x and y as two variables representing some population. Regression equation explains y in terms of x. We may write the behavioral equation in this context as y equal to alpha plus beta x plus u. In this specification, expectation of y given x or conditional expectation of y given x is equal to alpha plus beta x. Expectation of y given x may also be termed differently. Here expectation of y given x is equal to alpha plus beta x. Then we may write the equation as y is equal to expectation of y given x plus u. Let us summarize. In the essence, we may compare two models, because in the regular econometric model there is a sub model. The sub model is called empirical model, the main model is econometric model. The empirical model is otherwise called as empirical regression equation, the econometric model is called theoretical regression equation. The empirical model is deterministic by nature, whereas the econometric model is stochastic in nature. The empirical model is denoted as alpha plus beta x, whereas the econometric model is denoted as alpha plus beta x plus u. The empirical model tries to explain the expected value of y, whereas the econometric model tries to explain actual observations of y. In the empirical model you do not have u, whereas in econometric model you have u. The types of regression models are based on the empirical representation of the regression equation. The regressions are named with respect to the number of independent variables and functional description of the regression equation. Now let us compare or classify the regression equations based on number of independent variables. If a regression model contains only one independent variable, then that model is called the simple regression model. On the other hand, if the model contains more than one independent variable, then the model is called multiple regression model. Simple regression is the study of dependence of one variable y on another variable x with a view to predict the average value of the dependent variable in terms of the fixed value of the explanatory variable. Let us try to typify the regression models based on the number of independent variables. The model simple regression model or bivariate regression model, or otherwise called two variable regression model, can be easily represented as y is equal to alpha plus beta x plus u, where alpha is the intercept term and beta is the slope term, and alpha and beta are parameters, and u here is a random error component. And similarly, the multiple regression models are represented as y is equal to beta 0 plus beta 1 x 1 plus beta 2 x 2 plus u, where beta 0, beta 1 and beta 2 are parameters and u is a error component. The generalized model of multiple linear regression model can be represented as y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 etc. plus beta k xk plus u, where beta i's are parameters and xi's are independent variables. Now, let us see the typology based on the functional form of the regression model. The regression model could be broadly categorized according to the functional form of the regression function. The functional form could be related to independent variables or parameters. The functional form according to variable can be seen first. The natural reference to function is made on independent variables. The common characterization is done with respect to the geometrical characteristics of a regression curve, and that is called linear. There are other forms that are non-linear, curvilinear form. If the degree of the regression equation is 1, then that regression model is called linear and it will represent a line geometrically. Otherwise, that model is called non-linear. They will be represented as a curvilinear in the geometrical plane. However, a linear specification is broadly defined as y or some transformation of y expressed as a linear function of x or some transformation of x. In this sense, y equal to alpha plus beta x is obviously linear. Let us take the case of y equal to alpha x power beta. In this case, if you take log both sides, it becomes log y is equal to log of alpha into x beta. This can be further reduced to log alpha plus beta log x, where alpha dash is equal to log alpha and x dash is nothing but log x. Now, this is linear in logarithm of y and logarithm of x. Similarly, take the another case. Here y is equal to exponential of alpha plus beta 1 by x. In this case, if you take log both sides, it becomes log y is equal to log of exponential alpha plus beta 1 by x. This can be reduced to log y is equal to alpha plus beta 1 by x. Here in this case, this can be written as alpha y dash is equal to alpha plus beta x dash, where y dash is equal to log y and x dash is equal to 1 by x. Apart from geometrical definition of the linearity, as stated in the above definition, lot of other functional forms can also be defined as linear function or linear regression. For example, y is equal to alpha plus beta x plus gamma x square can be taken as a linear function if x squared is taken as one independent variable. Let me say x dash. Similarly, y is equal to a into x1 power alpha x2 power beta. If you take log both sides, it becomes a complete linear function. So, the linearity as assumes a larger and broader definition in econometrics. Any transformation of y or transformation of x1 would also be written as linear. If that is possible, then those equations are also called as linear equations. In some functions, such transformation may not be possible. Let us see some of the cases. These functional classifications are done according to the parameters. The functional classification of regression models done with respect to regression coefficients will present another dimension of linear and non-linearity in the regression models. If the maximum degree of coefficients in each term of the regression is 1, then that regression equation is called linear in parameter, or otherwise it is called non-linear in parameters. Linearity in regression means linearity in parameters and not linearity in variables, because the linearity defined in terms of variables can be converted into linear regression models as stated previously. Because of the special situation, we are going to define the linearity in terms of parameters, not in terms of variables. Classical linear model is concerned with models with linear parameters. These equations may or may not be linear in variables. Some models, as we see before, look non-linear, but an algebraic manipulation may convert that into a linear model. For example, y is equal to beta 0 plus beta 1 x 1 is a linear equation, linear regression. See the case here. Y is equal to 1 minus rho beta 0 plus beta 1 x t minus rho beta 1 x t minus 1 plus rho y t minus 1. This equation, there are in the first term you have two parameters, rho and beta 0. In the third term you have two parameters again, rho and beta 1, and these regression model, they are called non-linear with respect to parameters. This kind of linear equations, this kind of equations can never be converted into linear form at any cost. So, we call these equations as non-linear, and if you take the other example, whereas where we write y equal to beta 1 plus 0.75 minus beta 1 whole power e into e power beta 2 x minus 2. This variable is also this equation, the second term, the coefficients will not be linear, and so this model is also not linear according to the definition in the regression model. Regression models also require a distinction between the mean and a conditional mean. Though we discussed some of it in our previous review of statistics part, let us see the diagram given below. In the diagram you have x and y axis and the data presented as a scatter plot. The middle of the scatter plot, a line is drawn. Now, let us see how the average, the mean and the conditional average or conditional mean is defined. Expectation of y is considered the arithmetic mean of all the possible y observations. You take all the observations presented in the scatter plot is taken and you find the average of it. In the above scatter plot, the average of ordinate values of all the points in the scatter plot would give the global mean, the expectation of y. The conditional mean or expectation of y given x is equal to xi, or simply expectation of y given x is called the conditional average. Here the average is calculated only for the y corresponding to the observations on x I. In other words, the scatter points that has abscissa equal to x I alone are considered in finding the conditional average of y in this case. The average of the ordinate values of those points is called the conditional mean or conditional average. Such measures may also be defined for the variance and covariances. Now, let us see simple regression model and some of the notations used in that regression model. Once a specification equation has been decided upon, this equation is called theoretical or population regression function. As we stated, we will take the simplest of the regression models here represented as y is equal to alpha plus beta x plus u. This equation is both simple and also linear, and so this equation is called simple linear regression model. We may write the simple linear regression model in terms of the observations also. In the cross section observation regression models, we write the regression as y I is equal to alpha plus beta x I plus u I, where I varies from 1, 2 and up to n. Here n is the population size. Similarly, the time series data models would be represented as y t is equal to alpha plus beta x t plus u t, where t varies from 1, 2 and up to t. Similarly, if the data is a time series data set, then the time series models can be represented as y subscript I t is equal to alpha plus beta x I t plus u I t, where I varies from 1 to n and t varies from 1 to t. This line will pass through the centroid of the data, namely x bar and y bar. This regression line is a locus of conditional means of y, that is expectation of y I given x I, and so is equal to alpha plus beta x I. When we take all the possible values of x and y, then we get the population regression function. The empirical population regression function may also be written for that. For a given sample, we may draw a regression function, and this may be called sample regression function or otherwise called SRF. For each sample, there may be a corresponding regression function. All those regression functions are called sample regression functions or SRFs. The sample regression functions are denoted as y I is equal to alpha hat plus beta hat x I plus e I. Here alpha hat and beta hat are estimated regression coefficients, and e I is the error term defined for each of the observations in sample. The diagram below represents the SRF and PRF in one single graph. The x and y axis are given, and the thick line is the PRF or conditional expectation of y given x I, that is equal to alpha plus beta x I. The SRF is denoted as y t hat is equal to alpha hat plus beta hat x I. The error terms is also mentioned, whereas actually for the given x I, you have corresponding observation yi, the gap between the y hat and y is denoted as ei, whereas the gap between the conditional expectation of y given xi and yi is taken as ui. So, this diagram clearly explains what is ui and what is ei. Now, let us see some of the assumptions made on the classical linear regression models. The linear regression model is based on certain assumptions, some of which refers to the distribution of random variable u, some to the relationship between u and the explanatory variable, that is x, and finally some refers to the relationship between the explanatory variables that will come only for the multiple linear regression models. Assumption 1, mean of ui is 0 or the expectation of ui is equal to 0. The first condition is that the expected value of the disturbance term in any observation should be 0. Sometimes ui will be positive, sometimes negative, but it should not have a systematic tendency in either direction. If an intercept is included in the regression equation, it picks up any such systematic tendencies, but constant tendency in y not accounted for by the explanatory variables included in the regression equation. So, now expectation of ui given xi is equal to 0, that is mean of the ui is 0. Let us see the diagram here. In this case, for every observation, the mean or average of the stochastic variable is perfectly is equal to 0 in the diagram. Assumption 2, variance of ui is constant or homoscedastic. The population variance of the disturbance term should be constant for all observations. Sometimes the disturbance terms will be greater, sometimes the variance in the disturbance terms may be smaller, but there should not be any a priori reason for it to be more erratic in some observations than in others. Therefore, variance of ui given xi is equal to expectation of ui square given xi is equal to sigma u square, that is a constant. Look at the diagram below. In this diagram, all the distributions of ui for different observations are the same. The variance or the spread of the distribution is same across all the observations of xi. Assumption 3, covariance among ui is 0 or there is no autocorrelation. This condition states that there should be no systematic association between the values of the disturbance term in any two observations. The values of the disturbance term should be absolutely independent of one another. This can be stated as expectation of ui uj is equal to covariance of ui uj is equal to 0, where I not equal to j. Take the case of the diagram here. In the first diagram, in the leftmost graph, you can see the values of ui is scattered around the middle point, and that does not have any pattern in that, and so this is uncorrelated. In the middle, you have a pattern that shows the upward, and this is positively correlated, and the rightmost graph you can see a negative correlation. Assumption 4, UI is IID, that is independently and identically distributed, and every UI follows normal density with 0 mean and sigma square variance. Stochastic error tend to be Gaussian or normal in their distribution. That is because the stochastic error is most often the sum of many random errors. When we add many random errors together, the disturbance of their sum looks Gaussian, as shown by the central limit theorem. A stochastic error is added to a regression equation to introduce all the variations in y that cannot be explained by the included x's. The justification for the assumption depends on the central limit theorem. In essence, this states that if a random variable is a composite result of the effects of a large number of other random variables, it will have an approximately normal distribution even if its components do not, provided that none of them is dominant. The disturbance term U is composed of a number of factors not appearing explicitly in the regression equations. So, even if we know nothing about the distribution of these factors, we are entitled to assume that they are normally distributed. The random variable is normally distributed. Look at the diagram below. Each of the distribution of U is represented, and those UIs are identically looking and have the average 0, and all the variances are looking the same or homogeneous. We may call it sigma u square. Assumption 5, x and u are not correlated. The disturbance term is not correlated with the explanatory variable. The u's and the x's do not tend to vary together, their covariance is 0. Symbolically, covariance of x and u is equal to expectation of xi minus expectation of xi minus expectation of xi, and ui minus expectation of ui is equal to 0. A conceptually easier and computationally more convenient assumption could be that the independent variables are assumed to be non-stochastic, that is, does not have a random components in it. Therefore, the covariance of x u is equal to sigma xi expectation of ui minus expectation of ui is equal to 0, as expectation of ui minus expectation of ui is equal to 0. Assumption 6, the independent variables are measured without error. UI is conceptualized to represent the influence of omitted variables and errors of measurement in yi's. Therefore, the independent variables are assumed to be error free, which cannot be accounted in the regular regression model. Assumption 7, the independent variables are not perfectly linearly correlated. The number of observations must be greater than the number of independent variables. Look at the diagram below. That diagrams are called Ballantyne's Venn diagram, which indicates the correlation between different independent variables. In the first case, two variables are not correlated. In the second diagram, you can see two variables are correlated, but little less. The amount of correlation, the third, is bigger than the second one, and the fourth one is showing increased correlation, and the fifth one shows furthermore correlation, and the last diagram shows the perfect correlation. In the diagram, R squared equal to 0 for A and R squared is equal to 1 for F. The intersecting portion is said to represent the shared variance of x and y. So, that is how the explanation is done. If there is more than one explanatory variable in the relationship, it is assumed that they are not perfectly correlated with each other. Indeed, the independent variables should not even be highly correlated. If the correlation is perfect, then it would make the estimation impossible, or else even if they are highly correlated, it would make the statistical estimate highly inefficient. Assumption 8. The regression model is correctly specified and the regression model is linear in parameters. No specification error. The model used to test an economic theory is correctly specified. The specification error is defined in terms of three dimensions. One, enlisting of variables to be included in the model, the functional form proposed for the model, the probability assumptions made for the model. The model should contain all the variables required by the theory and should be linear in parameters. Assumption 9. The macro variables should be correctly aggregated. If the aggregative variables, the sum of the individual items, are used in the model, it is assumed that the appropriate aggregation procedure is used in compiling the aggregate variables. For example, in the estimation of aggregate consumption function C is equal to alpha plus beta y, the aggregate consumption and aggregate income are appropriately combined. Assumption 10. There must be sufficient variability in the values taken by the dependent and independent variables. That means x and y are quantitative. The variation in y, variation in both y and x is essential to use the regression analysis as a research tool. Assumption 11. The relationship being estimated is identified. The variables that are considered in the economic theory are assumed to have a unique mathematical relationship. Only if this condition is satisfied, the coefficients resulting from the regression model would truly predict the population regression coefficient. Let us summarize what we have studied so far. In this session, we started off with the regression model and its components. Then I classified the regression models by the number of independent variables and the functional forms. Then we defined what is simple linear regression model. Then we talked about the assumptions made on the random error term. We discussed about 11 assumptions made on the classical linear regression model error term. Thank you.